In this section, we are learning some more laws or properties of logarithms, and we are addressing State Standard 14. Students understand and use the properties of logarithms to simplify logarithmic numeric expressions and to identify their approximate values. And we're addressing State Standard number 11, that these three simple laws of logarithms we're going to learn today, you must also be able to prove them. So let's jump right in and start with the first law of logarithms. If we have positive numbers x and y, where a is any positive number other than 1 positive integer, this is true. The log of the product x times y base a is the same as the log of x base a plus the log of y base a. If I were to paraphrase this law, I would say logs turn multiplication into addition. Let's look at some numerical examples to try to help us understand this. The log of 9 times 27 base 3 is therefore the same as the log of 9 base 3 plus the log of 27 base 3. Now let's try to simplify this in our head. 3 to what power is 9? Because remember, logs are looking for an exponent. 3 to what power is 9? Answer to that is 2. This question, 3 to what power is 27? Well, 3 to the third power is 27. 2 plus 3 is 5. So we've got the log of 9 times 27 base 3. The answer to that exactly is 5. All right, what we want to be able to do is use this property forwards and backwards, from left to right and from right to left. It's an equal sign, so we have to know both directions. So going the other direction, if we have the log of 20 base 5 and we're adding the log of 3 base 5, according to this, we can make it the product of 20 times 3 and then take the log of that product base 5. So that's how we're going to rewrite it. 20 times 3 is our product, and we're going to take the log of that base 5. Now 20 times 3 is 60, and we don't quite yet know how to get the log of 60 base 5. We could estimate and say 5 to what power is 60, but we don't have an exact value. 5 to the second power is 25, 5 to the third power is 125. It's somewhere between 2 and 3. We'll get to that with our calculators a little bit later in the chapter. All right, our second law, or property of exponents, says this. If we have the log of a number raised to a power, base a, that's the same thing as the power times the log of that number, base a. Fine print, x is a positive number, any number p, any logarithm base a. If I were to, before we go ahead, translate this, kind of paraphrase it into words, I would say logs turn exponents into multiplication. And if you think of the order of operation, logs are going to move them one level down. Exponents are moved down to multiplication. In law 1, we had multiplication that was moved down to addition. So let's look at some numerical examples of this. The log of 9 to the negative 5th power base b, let's express it as a product. In other words, let's just put some numbers in this property and practice it. So that's the exponent negative 5 times the log of this number 9 base b. Since we don't know what the base is, we can't simplify that any further than that for now. Here I've got the log of the 4th root of 5 base a. We're just going to simplify that and rewrite it. Let's write the 4th root of 5 as 5 to the 1/4 power. That's something we have to remember from a previous lesson, that if we have a rational exponent, the base is my radicand, the denominator of my rational exponent is my root index, and the numerator is the power we're raising it to. Now I've got the log of a number raised to a power. That's the same thing as the power times the log of that number 5 base a. Here's our third law of logarithms. X and y are positive numbers. Any logarithm base a says we've got the log of a quotient, x divided by y base a. That's equal to the log of the numerator base a minus the log of the denominator base a. So if I were to paraphrase this in words, I would say that logarithms turn division into subtraction. Again, one level lower on the totem pole of the order of operations. Logs turned exponents into multiplication, multiplication into addition, and division into subtraction. So for example, 4.5, we want to rewrite the log of 19/5 base b as the difference of two logs, and that's this law 3 we're practicing. And so that's the log of the numerator, 19 base 3, minus the log of the denominator, 5 base 3. All right, what we want to do is to try to take those three properties or laws and use them all in one problem. So I've got the log of the fourth root of xy over z cubed base a. We want to rewrite this so we've got a log of x, a log of y, and a log of z. So I got to practice all three of these laws together. Fourth root, remember again we said that's the same as the rational exponent to the 1/4 power. So the radicand is my base, my root index is the denominator, and I'm raising it to the first power because there's nothing written there, so that's my numerator. Now I've got the log of a number raised to a power base a. That's the same as that exponent 1/4 times the log of my quotients, xy over z cubed base a. However, when I have a quotient, the log of a quotient is the same as the log of the numerator, xy base a, minus the log of the denominator, z cubed base a. And I had to put brackets or parentheses around this because this 1/4 is times that whole expression, and now that it's become a binomial, I need to make sure it gets distributed out. All right, going a little further, here we've got the log of a product. And we know that the log of a product is the same as the log of the first factor plus the log of the second factor to that same base. And while we're at it, the log of a number raised to a power is that power 3 times the log of z base a. And to wrap this up, if we will distribute out 1/4, we'll have our solution. So it's 1/4 the log of x base a plus 1/4 the log of y base a minus 1/4 times 3, so that's 3/4 the log of z base a. So the direction said write it as in terms of log of x, log of y, log of z. I've got a log of x, log of y, log of z. All right, now that was fun. So much fun. Let's drive that problem, or one like it, in reverse. We're going to take a log of x, log of y, and log of z and write it as a single log. Kind of like the previous example in the reverse order. Again, you can't get your driver's license till you can drive that car forward and backwards. So going backwards, if we have a product, some number times a log, that number is my exponent. So this is the log of x to the 1/2 power base a. The 7 is times the log, so that's my power of y, so that's the log of y to the 7th base a. Now, nothing logs yet, but I thought you might be more comfortable saying x to the 1/2 power as the square root of x. Remember rational exponents, the base is the radicand, denominator of the rational exponent is our root index, the numerator is the power that's being raised to. That's the only change I made here. From there, we're subtracting two logs with the same base. Must have the same base to do this. So that's the same as the log of the quotient, square root of x divided by y to the 7th, in order as we go from left to right. And then the next step after that, I'm adding two logs same base, so that means I can take the log of their product. So z over 1 goes in the numerator. So that's the log of the square root of x times z over y to the 7th base a. And that's written as a single logarithm, using those three properties backwards. All right, what we're about to do now is do approximate numerical values for logs. And in your book, they make this way too easy. But they're saying the log of 2 to some mystery base is approximately 0.301. Now, you see the log of 2 and the log of 3 base 10 so frequently that you memorize the log of 2 is actually 0.3010 and the log of 3 is 0.4771. So the book's not being very tricky because this is base 10, and you could guess this by using the log base 10 button on your calculator, which we'll learn in a future lesson. I'm pointing that out because I'm not as obvious as the book. So when you see a question like this on the test, you will not know what base this is. and I will not use base 10, so you cannot just push buttons on your calculator to avoid doing this the way we want you to. These are exercises to practice the 3 laws of logs. Given the fact that the log of 2 is 0.301 and the log of 3 is 0.477, what's the log of 6? Well, don't forget we can write 6 as 2 times 3. And don't forget, if we have the log of a product, that's the same as the log of the first factor plus the log of the second factor, same base. And now we're going to substitute. We know the log of 2 is 0.301. We know the log of 3 is 0.477. Add those 2 decimals together, and the log of 6 to this mystery base is 0.778. How about the log of the square root of 3 base a? Well, let's remember that the square root of 3 could be written as 3 to the 1/2 power. And the log of a number raised to a power is the same as that power times the log of the number 3. They told us the log of the number 3, and that's 0.477. Take half of that, multiply it by half, divide it by 2, and the log of the square root of 3 base a is 0.2385. So again, just numerical exercises, nice and simple, to practice those 3 laws of logs that we need to know. All right, the log of 2/3 base a. Well, that's the same as the log of, when we have the log of a quotient, the log of the numerator minus the log of the denominator. We know the log of 2, we know the log of 3, substitute those in and subtract. So the log of 2/3 is negative 0.176. How about the log of 5? Now you could think about this, you could stare at it, but you'd have to write 5 in terms of 2 and 3. And some of you are thinking, well, 5 is 2 plus 3. But we don't have a law of logs that says the log of 2 plus 3. So actually, can't do this one. Can't write 5 as 2 to some power or 3 to some power, or 2 times 3, or 2 divided by 3, or 3 divided by 2. Can't do that. All right, now this one, be careful. I want to compare and contrast 7c to 7e. 7c is the log of 2/3 base a. 7e is the log of 2 base a divided by the log of 3 base a. There is a law for 7c, but not one for 7e. So what you have to do is look up the log of 2 first, look up the log of 3 next, and divide those decimals with your calculator. So 0.301 divided by 0.477 is approximately 0.63. All right, now we want to estimate without using our calculator. Log of 5 base 2 is between what 2 integers? Well, how do we do that? Well, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So 2 squared is 4, 2 cubed is 8. 5 is somewhere between 4 and 8, so it's somewhere between 2 to the second power and 2 to the third power. Remember, log is looking for exponents, so it's somewhere between 2 and 3. It's 2 point something. What that something is, we don't quite know yet. We're just going to call it 2 point something for now, and leave that till we get to use our calculator a little bit later. All right, well, we have learned the definition of these law of logs. We've practiced them with numeric and non-numeric examples. And now the state standards and La Cañada says we need to be able to prove these logs. Prove these laws of logarithms. So let's go to law number 1. We have the log of m base b is equal to x, and the log of n base b equals y. So let's rewrite that in exponential form. B the base to the x power equals m. B the base to the y power equals n. If that's true, what if we multiply m times n? Well, we get b to the x times b to the y by substitution. B to the x is the same as m, b to the y is the same as n. When you're multiplying, the bases are the same, you keep the base and add the exponents x plus y. Well, now let's take mn equals b to the x plus y power, And let's forget about this middle section. Let's take the log of both sides of that equation, base b. Yes, it's possible to take the log of both sides of an equation as long as it's the same base. And on the right side, you're saying, well, how did we go from the log of b to the x plus y power base b to just x plus y? Remember, log is looking for an exponent. B to what power is b to the x plus y power? Well, that's x plus y. So, therefore, the log of m times n base b is equal to, now let's substitute again. Remember, x was the same as the log of m base b. Y was the same as the log of n base b. Substitute that in, and we just proved the first law of logs, that the log of a product is equal to the law of the first factor plus the law of the second factor, same base. Alright, we need to prove the law number 2 and law number 3. So again, we're going to say, well, let's let m base b equals x. Let's let the log of n base b equals y. If, again, we rewrite those as exponents, b to the x power equals m, b to the y power equals n. Alright, from there, here's how we're going to progress with law number 2. What if we took m and raised it to some power k? Well, first of all, m is the same as b to the x power. So by substitution, this would be b to the x power to the k power. And when you have a base raised to a power, you multiply those. So that's b to the kx power. So m to the k power is the same as b to the kx power. If we take the log of both sides of this equation, forget the little step in the middle, the log of m to the k power is the log of b to the kx power, both base b. On the right-hand side, we can eliminate the log by answering the question. B to what power is b to the kx power? Answer to that is kx, because log is looking for an exponent. And let's again substitute. We're going to leave k alone, but on the right side, x is the same as the log of m base b. And we've just proved that if you have the log of a number raised to a power, that's the same as the power times the log of that number, same base. Alright, 2 proofs down, 1 to go. We're going to start out the same way. Let the log of m base b equals x. Let the log of n base b equals y. In that case, we can rewrite those as b to the x power equals m, b to the y power equals n. From there, what if we divided m by n? M divided by n, by substitution, m is the same as b to the x power, and n by substitution is b to the y power. And we know that when you're dividing and the bases are the same, you keep the base and subtract the exponents, numerator minus denominator. So m over n is b to the x minus y power. Forget about this middle step momentarily. Let's take the log of both sides of this equation on the left and on the right, both base b. Log of m divided by n base b equals the log of b to the x minus y power base b. Log is looking for an exponent. What exponent of b is b to the x minus y power? The answer to that question should be obvious, x minus y. Okay, once again, we're going to do a substitution. X is the same as the log of m base b, and y is the same as the log of n base b. And we have just proved that the third law, that the log of a quotient, m divided by n, is the log of the numerator minus the log of the denominator, both to the same base. Very crucial that we know these properties or laws of logs, know how to use them, know how to prove them.